Okay, so we're going to get started on section 2.5, and the title of this section, or in this section, we're going to be talking about a special type of equations referred to as Diophantine equations. These equations actually are given in several books written by Diophantinus of Alexandria, who lived about in 250 AD. He wrote several books actually, and all of these are type of question-answer, books. He would give an equation, and he would give a solution for this equation, and give some equation without solutions. All right. So the objectives of this section is first we need to know what do we mean by a Diophantine equation. Then we're gonna look at the Diophantine equations, actually linear Diophantine equations, first on one variable. Then we're going to look at actually Diophantine equations of degree n, or order n, in one variable. And there are two questions that we're going to be interested in studying, Diophantine equations, or any type of equation, basically, is to give a necessary and sufficient conditions for solvability. In other words, when an equation, or a Diophantine equation in our case, is solvable, okay? And then to give a method for finding the solution set, means all solutions of the equation. Then we're going to move into a linear Diophantine equation in two variables, all right? And again, we're going to be discussing the same issues as we have in part 2 in here. Then we're going to look at those solutions which consist of positive solutions, which we need to define, of course, and look at some applications. Then we're going to end by looking at linear Diophantine equations in n variables. And again, we would like to give necessary sufficient conditions for their solutions and give a method of finding the solution set. All right, so let's just start with the simple objective is what is a Diophantine equation. A Diophantine equation is an equation, all right, regardless of the number of variables and what type of an equation is it, all right, whose coefficients are integers, and we are interested in solving the equations, and the solution that we seek is integral, means integers. So we could give a sort of a definition for this by a Diophantine equation. We mean an equation whose coefficients are integers and we are interested in the integral solutions, or integer solutions, solutions of the equation. So there are two key words in here, the coefficients being integers, okay, and the type of solutions that we would like to, or we look at, or when we talk about an equation being a Diophantine equation, is the solution to be integer, okay. So these are the sort of the two keywords that define or characterize what the Diophantine equation is. So let's just start with the simplest type of Diophantine equations, that is the Diophantine equations in one variable. And let's start with the linear one. Okay? Going to start with Diophantine equation. Let me say actually linear. Let me start with the word linear. Diophantine equation in one unknown or one variable. This is similar to any kind of equations that a linear equation in one variable that you see in algebra. So it is an equation which has this form. So in here, of course, we want the where A and B are integers, and of course, we want to require A not to equal to 0. All right, we require that A is not equal to 0. Now we know that the solution of this, if you even think about it as a general equation in one variable, the solution is x equal b over a. And since a does not equal to 0, so this makes sense. Now the question is, when b over a is an integer, all right? And this is going to give us the necessary condition for the equation to be actually solvable, all right, in having, integral solution or integer solution. So the answer is, of course, if A divides B. B actually. Okay. So, and in this case, and if this condition is satisfied, then the equation has, in fact, a unique solution. Namely, x equal b over a. Now, this is, because of this implies that b is equal to a sum times k for some k in z. So that's what does it mean for a divides b. And with this, then the solution is going to be actually x equal to k. All right? So in this case, which is of course an integer. And it's unique because the divisibility gives me a unique k in here that actually satisfies this equation. All right, now the question is this sufficient condition? Means if A divides B, is it true that the equation has a solution and the solution is unique? Of course, it's not very hard to see that answer is yes. And in fact, the argument that I wrote about divisibility there is what makes it true. So in other words, on the other hand, if in the equation ax equal b we have, or if this has a solution rather, if the equation, yes, has an integral solution, then A divides B. Let's see the reasoning for this, and we're going to come up actually from this with a theorem that gives us a necessary and sufficient condition. All right, well, here we are assuming that the equation does have an integral solution. Let's call this, let x sub 0 be an integral solution of ax equal b. This implies that x sub 0 is, of course, is an integer, and ax sub 0 equal b, actually this is a true state, through equality. All right, well, from here, this means that actually A divides B, right? Because you could express B as a multiple of A, all right? So this is it. So what we have accomplished in here is the proof of the following theorem. So I just want to put this information in here in a form of a theorem. Here is the theorem. Which basically states exactly what, what we said in here. Let A, B being integers, A does not equal to 0, then AX equal B, this equation has a unique integral solution if and only if A divides B. And since it's a unique solution, actually the methods that you learn for solving the equation in algebra, okay, very, very simple algebra, provides a method for solving this. All right. Next, let's move into Diophantine equations in higher order or higher degrees. Okay, not linear anymore. So the proof of this is actually just the discussion which we actually presented. All right. So let's look at next. We consider a Diophantine equation or Diophantine equations, put it this way, in one variable of degree n. Okay, so this equation looks like this: a sub 0 plus a1. Let me see in which way I want to write this. Let me start with an actually. Put it in the equation anyway, so an xn plus an minus 1 n minus 1 plus a1 x plus a sub 0 is equal, sum actually is equal to 0. Where in here all the ai's does belong to Z, and the AN, we don't want it to equal 0 to call this equation of degree n. All right? So once again, we would like to know under what conditions this equation has an integer solution. Okay? Remember, these kind of equations, even when we deal with real numbers, all possible solutions in the real or the complex is a very, very hard, right? Unless it's a quadratic, maybe cubic, maybe the quartic is fourth degree. And after that, exact methods of solution are not available. All right? However, when we concentrate on, or we only consider the integer solution, integral solutions, the situation is much simpler. Okay? Now, unfortunately, when we consider equation in more than one variable that are quadratic or cubic, which are Diophantine equations, their solution is very, very complicated and very, very involved. Okay? So it happens that because of one variable case. All right, let's assume that this again has a solution. Okay? Let us assume that x sub 0 is an integral solution to the equation. Now, what we would like to find the necessary condition first, and hopefully it will be sufficient, and that is a whole. So what does this mean? This means that the x sub 0 is an integer. All right, that's what we mean by an integral solution. And it would satisfy the equation. So this would imply that an x sub 0 n plus an minus 1, x sub 0 n minus 1, and so on. In other words, now we have a numerical value, and this is equal to 0. Or, if I take the a sub 0 to the other side, we can say this is equal negative a sub 0. And now in this side of the equation, in this side of this, actually the right side, it's not an equation anymore, okay? It is this expression. I can factor out an x sub 0. This becomes x sub 0, then we have an x sub 0 n minus 1 plus a n minus 1 x sub 0 n minus 2 up to a1. So, if this equation has an integral solution, then we have this relation that's satisfied. And what does this mean? This means that x sub 0 actually must divide, all right, a sub 0, or negative a sub 0, so it is a sub 0, right? Because we can write a sub 0 as an x sub 0 plus this, and remember that all these coefficients are from z, as well as x sub 0 to all these different powers, so this is an element in z. So in other words, this becomes a necessary condition. So this is a necessary condition for solvability of this equation of the equation in integers, okay? So this equation does have a solution. That solution must divide the constant coefficient, okay? The constant coefficient of this polynomial, or if you take the constant coefficient to the other side of the equation, it will divide the right-hand side of the equation. Unfortunately, this is not a sufficient. Means if we have, x, in other words, It doesn't mean that if x sub 0 divide, if let me put it in a different one. Maybe look at an example first, and then we can see what I wanted to say, basically. All right, so let's look at this example. All right, we look at an example in here, quick example. This is a 10th degree equation. You need to find the solutions of this, integral solutions. Okay, so if this equation, and that's the difference, if this equation has integral solutions, then let's say, let me say if this equation has an integral solution, just one, okay? It has integral solution, say x sub 0, then from our discussion, then x sub 0 must be a divisor of the constant term, which is 2. All right. Now the question is, what are, and of course, this x sub 0, it's going to be an integer. So what are the divisors of 2? This implies x sub 0 is equal plus minus 1 plus minus 2. Because these are the only actually divisors of 2. The only way we could write 2 as the product of an integer and 2 is this. All right. Now, we can check which one of these. This is where we are saying it's not sufficient condition. Means not all of these are solution. Okay, so this is not all of these. Are solutions. But if it is sufficient, then all of these will be solutions. But now, we restricted our attention to only 4 possibilities. And by trial and error, or by substitution, in other words, by substitution, we found that x sub 0 is equal to negative 1 is the only solution. Only integral solution. Now remember this equation when we want to solve it over complex numbers, allow complex numbers to be solution, it has 10 solutions, okay? And not necessarily these are distinct, but 10 solutions based on, or if we are counting what we call multiplicity. Now you could check this one in here, of course, and we double check. So this is 1, this is minus 1, and this is minus 2 plus 2. I think this gives you a 0, right? Yes. So it does give 0. All right. Now we need to move into Diophantine equations, linear Diophantine equations in 2 variables. In fact, Diophantine equations that are not linear are very complicated to solve. In general, there are some few cases, special cases that we will look at. One of them is like what we call the Pythagorean truth. Okay, But there are some Diophantine equations. It actually took hundreds of years to figure out that they are not solvable. Okay, this is what we call Fermat last theorem. All right, so here we want to talk about linear Diophantine equations in two variables. And in particular, we are going to look at this part with A, B, and C. These are integers, and we don't want A and B to be equal to 0. Both of them I don't want equal to 0. So sometimes I set this as AB does not equal to 0. Then this equation, AX plus BY equals C, is called a linear Diophantine equation in two variables. Once again, we would love to have a necessary and sufficient condition for their solvability, which remember that we are interested in solutions that are integers, means the x and the y are integers, and they satisfy this equation. And we would like to find all of those, not just one solution if there are more than one solution. First of all, actually, it is easy to find the necessary condition for the solvability. All right. Turns out that the equation is solvable or has an integer solution as an integral solution if and only if okay, so this means this is an sufficient condition. The greatest common divisor, D, which is equal greatest common divisor of A and B, divides C. So in simples means the D is going to divide C. We're going to formalize this in a form of a definition, in a form of a theorem, okay? But let's actually just, without being formal, without putting the theorem itself, actually show that this statement is true. So there are two things that we need to show. That is, if actually this equation has an integral solution, then this condition is satisfied. All right, D divides C and converge. Okay, so let's start by looking at the assume it does have an integral solution. Once in a while, when we state theorems or prove theorems, we might give a proof of a theorem or part of a theorem before we actually state the theorem. It's sometimes kind of nice to go with the flow. Or sometimes we write the theorem and say, here's the proof. All right? This time I'm not stating the theorem, but I'm proving this. Let us assume that x sub 0 and y sub 0, because the solution is an ordered pair, right? A value for x and a value for y. So I'm just going to specify like this. And y sub 0 is a solution it's an integral solution, okay? Even if sometimes we don't write this, when we hear what the type of equation we deal with are, those with integral solutions. So these are integral solutions to ax plus by equals c. Well, what does this mean? This implies that we have ax sub 0 plus by sub 0 is equal c. Actually, this equality holds. This equality holds. It's not anymore an equation. This is two integers are equal to each other. On one side is integer, on the other side is c. All right. Now, let D be the greatest common divisor of AB, and this implies that D divides A and D divides B. And this in itself implies that A is equal dr and B equal ds for some rs in Z. Now let's substitute in these values of A and B in this identity in here. So this ax sub 0 plus by sub 0 equals c becomes is dr x sub 0 plus, and remember that A and B are not 0, okay, so everything goes nice in here. ds y sub 0 is equal to c. All right, so still this is an identity. Now, I can factor a d out, and then we end up with this. And this implies, because I am expressing C as the multiple of D, so this implies that D divides C. So yes, if we have an integral solution, then the condition is satisfied. Now we're going to go conversing, okay? So let's assume, we actually take all of this out and write the statement. Conversely, assume that B divides C. And we need to show ax plus by equals c has an integral, has at least one integral solution, an integral solution. All right. Once again, let me see in which order I want to go in here. All right. So we know that since D is the greatest common divisor of A and B, this implies there exists an x sub 0. Let me call this one actually a different letter here. We call it u sub 0. U sub 0, v sub 0 being integer, such that this is my Euclidean algorithm, where we can express D is equal A u sub 0 plus B v sub 0. All right. Now, we are given, since I don't have a C in here, as you can see. This is very nice sort of solution in here, but I don't have a C. In other words, to satisfy it. Now we need to use this condition. Since D divides C, this implies that C is equal some multiple of the, let's say, K D for some integer K. Now we can substitute for or multiply this equation. Let's multiply by C. So this becomes CD. All right, is equal to let me see, what I want to multiply. Let me multiply actually by K. I'm sorry. Let me multiply by K, not C, K. All right. But actually it's in front of me. I just want to get C. All right, so we're going to multiply by K. KD becomes A times KU sub 0 plus KV sub 0 and BC, K sub 0. I need a B. B times K V sub 0. Right. But KD is equal to C, so this is equal to C, and now I have a solution U sub 0 plus B KV sub 0. This implies that X sub 0 is equal to KU sub 0 and Y equal KB sub 0 is a solution. Because it satisfies, as you see, the one we took for the X, I call it X sub 0 to be KU sub 0 and so on. All right, so we have a necessary and sufficient condition. Now the question is, if this condition is satisfied, I know that in other words, if D divides C, then I know that the equation has at least one solution. And if it doesn't, means if we write this down before we move, then the equation has no solution. All right? No integral solution. So this is what we have. If D divides C, implies there is at least one integral solution. But if D does not divide C, there is no integral solution at all. None. Now, if we want to think about this geometrically, what does it mean for a linear equation in two variables? Let me just give a brief kind of discussion here. We know that you're given an equation ax plus by equals c, where a and b are not zero, neither one of them is zero. Then you get actually a straight line that is not neither vertical nor horizontal. So it's going to be actually intersecting, all right, the coordinate axes, the x and the y. All right. Now, this line, the points of it are actually the solution for this ax plus by equals c. Now, what this discussion is saying, if D, all right, is the greatest common divisor of A and B, does not divide C, then none of the points in this line, all right, which are infinitely many, actually are both integers. The x and the y are integers. It is possible that one value is integer, the other one must be not integer. Okay? So if D does not divide C, none of the points in here are called, actually we call such points where the X and the Y are integers because these are lattice points. Okay, if this, then none of the points on the line are both integers. So to put this in a technical language, you say that the points of this line, none of the points of this line are lattice points. So none of the points of the line are lattice points. So lattice points are the points which you kind of partition this, okay, by vertical and horizontal lines at the 1 and 2 and the 3, okay, the integral values, negative 1, negative 2 horizontally. And that intersection of all these lines, you know, their corner points basically are called lattice points, okay? On the other hand, if this condition is satisfied, what we have said so far, let's say we have in here, at least there will be one point in here for sure that it's a lattice point. Okay, it's y sub 0, where both the x and the y coordinate of the point on the line is an integer. Well, in this case, it's actually they belong to z plus plus. But let me put it as this. All right. Now the question is, are there any others other than this? In fact, there are infinitely many. Okay, and that is what we would like to prove. And we're going to put this is now in the theorem that we proved half of it. Okay, and then we're going to go to the other half and give the solution set, basically, for those Diophantine equation that has at least one solution or satisfy the D divide C condition. Okay, so this is the theorem. So this is theorem 2.9. And the statement is this: the Diophantine equation Ax plus by equals C. Now remember, means whenever we talk about a Diophantine equation linear like this, means A, B, C are integers, and A, B does not equal to 0. Neither A or B is equal to 0. This has a solution first. If and only if the greatest common divisor D, okay, divides C where D is the greatest common divisor of A and B. Moreover, if X sub 0, Y sub 0 is a particular solution, what does this mean, a particular solution? Particular solution is a numerical solution, okay? And we're going to find out sometimes if someone just being generous to you and gave you a solution, okay, using whatever method. then we're going to see that we can generate all other solutions, which we find what we call the general solution, use this particular solution. If somebody else gave you two other different solutions, then we call them particular, and again, we will use those to generate all solutions, okay? So particular because it depends on the numerical value presented to us, okay? Is a particular solution to the equation. Then the all solutions, or what we call, or the solution set, of the equation are given by this. X sub t, because we're going to label them with t, is equal this particular solutions, x sub 0 plus d over d times t, and y sub t is equal y sub 0 minus a over d times t, where t ranges over all integers, okay? And if I write this as a solution set, is just to put it inside braces like this, so it becomes a solution set. In particular, when t is equal to 0, we get actually the particular solution that is here. And when we change t, then we come up with different solutions. So all these solutions are different. You cannot have for one value of t is going to give me two different answers. It gives me one answer and one solution that corresponds to the t. And when you change t, you come up with other solution and so on and so forth. All right, we have improved half of this, which is this half. All right? That is, this Diophantine equation has a solution if and only if this. And now, once this condition is satisfied, okay, moreover, actually, in the case, actually, I need to precede this one by another statement. In the case where D divides C, we have this moreover, okay? Because if it doesn't, then this is invalid, all right? All right, so what we're going to do next, so we are having D divide C, means that at least I have one solution, and then we're going to learn how to find this solution. What I would like to do is to have the other solutions, and then show there is no others, other than the solution that actually given by this formula in here. All right? So let's assume that we have another solution, okay? So here's the second part of the proof. Second part of the proof. The moreover. So let's assume that x sub 0, y sub 0 is a solution. So this is given. And let us let x1 and y1 to be another solution. Let x1 and y1 be another solution. Of course, if we come up with, no, they must be equal to each other, means that x1 equal x sub 0, y1 equal y sub 0, means that a unique solution, and then whatever we're going to be doing, it should indicate that. But we're going to find out, no, it will actually be a different solution. We're not going to get the same thing. So if this is another solution, this implies it satisfies the equation. So this means this. We also have, since x sub 0, y sub 0 is a solution itself, ax sub 0 plus by sub 0 is equal to c. Now, these are numerical values for both of these. So both of these are equal to c, which implies that ax sub 0 plus by sub 0 is equal ax1 plus by1. So both of them are equal to c. Now we need to rearrange this, so let me subtract these to the other side. So this becomes a x1 minus x sub 0 plus b y1 minus y sub 0. So we have this is equal to 0. All right. Or we could actually rewrite this one in a slightly different way. We could say that a x1 minus x sub 0 is equal b. And let me switch these. This becomes y sub 0 minus y sub 1. And instead of having a negative, let me put it this way. And let's see what does this statement mean. Then we need to bring in the d to the picture in here. So we have this equality in here. Next, let's consider d is equal ab. This implies, again, a is equal a d r, and b is equal ds for some r s in z. Moreover, we know that the greatest common divisor of r and s is equal to 1. Remember, the reasoning for this is because the greatest common divisor of a over d, b over d is equal 1. And if you take what is a over d, this is equal to r, and this is equal to s. So the multiples of d, their greatest common divisor, is equal to 1. All right. Now let's go ahead and substitute in our last equation. This is at the very bottom in here. We're going to replace the a and the b by what they are equal to in terms of ds and dr. Okay. So let's substitute. So we're going to substitute for this a by dr in x1 minus x sub 0 is equal to b ds, and this is y sub 0 minus y sub 1. And remember, d is not equal to 0, cannot equal to 0. It's the greatest common divisor. So we can divide by d, and then we come up with this. This means that actually the r divides, okay, s times y sub 0 minus y1, all right? Because we could write this one as a multiple of r, which is what we have in here. And we have s divides the difference in the x's with a multiple of r, okay? So we have r x1 minus x sub 0. But we have since the greatest common divisor of these is 1, and R divides the product, and it doesn't have any common factor of S, this implies that it must divide the Y, the difference between the Y. So these are relatively prime, okay? So this divisibility implies that R divides only Y sub 0 minus Y1. Similarly, this one divides X1 minus X sub 0. Then we can say from here that Y sub 0 minus Y sub 1 is equal RT. All right, it's a multiple. And the same thing in here, which is S is equal or X1 minus X sub 0 is equal a multiple of S. We're going to see that actually the multiple then must be the same as T. So this is going to be S. All right, and from here we conclude that this implies X1, which is the solution, the new solution basically, or the other solution, is expressed as ST, and the Y sub 0, the Y sub 1 is equal to, we're going to actually bring this one in here, so it becomes Y sub 0 minus RT, where T, for some T, actually in Z. Supposedly here for some T in Z, or at a fixed T. Let me actually write this. It's not T belongs to, it doesn't range over all Z. For some T in Z. All right, so in other words, what we have done in here is we assume there is another solution, and we say this other solution must be related to the particular solution, as that particular solution was ST for the X and Y sub 0 minus RT. Also, we can write these, okay, in terms of the original variables, which is A, B, C, and D. But these are the kind of the other one. So that this becomes X sub 0. Remember the S, where is the S? Here is the S. So we can express that as B over D. Now remember that this is an integer because actually D is the greatest common divisor. So it's not a fraction. It looks like a fraction, but it's not. And Y1 is equal to Y sub 0 minus A over D. So these are the two solutions. Now I claim that actually if there is, and it's not hard to see, actually this would satisfy, of course, the equation, all right? Now the last thing we have to do is to show that if there is another solution, actually it must be of this form, all right? So let me put the last thing in here. Now let's assume, in other words, we have these values, okay? Consider a solution of this form. X is equal to X sub 0 plus B over D T. For a different value of T. Remember in here, it's a very delicate difference in here. There's one value of t that we gave us x1 and y1. I'm saying here, let t be anything. Consider a solution with like this and y equal y sub 0 minus a over d t, where t is any integer. If you want to put a numerical value, that's fine, but we want to do it even more general. Then I claim the solution, the expression above, consider, I don't want to say a solution, consider actually an x and a y value, and you know, expression for x and y of this form. Consider expressions for x and y of the form and I claim these are solutions actually. The expressions above are solutions. In other words, the previous one, let's see the delicate line between in the argument in here. In the previous argument, I said, let's assume we have x1 and y1 are solutions, and when we argued them, that they must be expressed in this form. Okay? Now I'm saying, let's take some expression of this form, all right, and show actually it also satisfies the equation. And all we have to do is here to substitute. Okay, so we sub in the equation ax plus by equals c, regardless of t, okay, where t is any number. Okay, then we have a times this x sub, the only thing I know is x sub 0, y sub 0 are solutions. That's the only thing I know. Okay, b over dt plus b, then y, I'm going to substitute for y sub 0 minus a over d t, and I want to check if we get c or not. Okay, so there's a question mark in here. I don't know, because I'm putting in numbers here, sort of, in the equation. Well, let's multiply. This becomes ax sub 0 plus a b over dt plus dy sub 0 minus b a over dt, and still I don't know if this will be c or not. All right, well, let's substitute for, or actually not substitute, just we're going to simplify this last expression. Let me put the ax sub 0 and the b sub 0 together. So we have, this is ax sub 0 plus by sub 0. All right, let's put the other stuff all together. Then we have plus, we have ab over d t, then we have minus ab over dt, and these cancel out, and the question is this equal to c? Yes, it is, because since this is a solution, since x sub 0, y sub 0 is a solution, then the ax sub 0 plus by sub 0 satisfy the equation. Yes, it is equal to c. Alright, so this is the proof of the theorem. So that the solution set expressed in terms of one solution. Now, the next thing that we would like to look at is how to find a single solution, a particular solution, because if we do, then we can find all solutions. All right? And that is the crucial point here. How to find a particular solution. But before we do that, let me put as actually a corollary to this theorem, which actually makes the calculations in our work easier. If greatest common divisor of A and B is equal to 1, then AX plus BY equal C. All right, so because the greatest common divisor is equal to 1, and of course 1 divides C, then this has a solution. All right, let's say X sub 0, Y sub 0. Then all solutions to AX plus BY equals C are given by this. X equal X sub 0. Remember, plus supposed to be B over D. Just be T. Y sub 0, Y equal Y sub 0 minus AT, where T ranges over all the entities. All right? Now, let's add. Of course, the proof of this is trivial because it's a trivial corollary, but it is very nice statement because it simplifies our life. Now, we need to discuss the methods of finding a particular solution. There are a couple of methods, or maybe 3 methods, one being trial and error. And this can be done in case the coefficients and the equation is very simple. Okay? So methods of finding a particular solution. Hence, all solutions. And some of these methods actually is going to give us all the solution altogether, and some of them give us a particular solution, and we can find the all solutions. Regardless of, what we always will be finding all the solutions. So let's just start with this one. Okay, so we're going to look at some examples. Let's look at 11x minus 33y. So we're taking a negative, the b is negative 33, is equal to 22. First of all, the greatest common divisor of 11 and 33, we don't need to take the negative, we don't need to take the positive in here. All right? So we know this is equal to 11, right? Now, we can actually reduce this equation. Use this equation by dividing, and this is where the corollary becomes the crucial, by dividing by the greatest common divisor of 11 and 33, which happens to be 11. Because we know that the equation does have, also I should have said this does divide 22 implies that the equation has a solution, at least one. And then we know it's going to have infinite limit. All right? All right. Now, to solve this equation, we can reduce the coefficient by dividing by 11. Because any solution for the reduced equation, when I divide by 11, it will be a solution for this. It's just you multiply back by 11. All right, and vice versa. If there is a solution in here, you divide by 11, it will be solution for this reduced equation. The reduced equation is going to be, comes x minus 3y is equal to 2. Very simple. In fact, we can guess what the solution is. So if you put x equal to, actually, let me see in here. All right, so x equal to 1 or negative 1, and y, let me see in here, 1 and 3 actually, 5 and 1, sorry. Oh my God. I don't want to guess actually, looks like. Okay, x equal 5, y equal 1 is a solution. Because the x sub 0, y sub 0. All right, just by plugging in back into the equation. Right, so this is just kind of hard guessing. Okay. Now, all solutions from here, we found that all the solutions for the reduced equation will be also solutions for the, the original equation. All right, or you multiply it by 11. So the solutions for the original equation, okay, let's see actually if you put in 5 in here, so this is 11 times 5, okay, because you can take an 11 out, minus 33 times 1, again, is this equal to 22 or not? The answer is yes, okay, so actually that solution for the reduced was also a solution for the origin. All right, now the general solution is going to be x equal 5, then minus 3t, and y, because the t, and we take it with the sign in here, and x or y is equal to 1 plus t, where t ranges over the integers. So the solution of this is given to be those solutions. All right, let me see in here if actually we need to take minus in here, sorry. Because we have to have minus 80, okay, so this is minus. All right, now from this one you can generate, numerical solutions by taking the t, all right, to be whatever, integer you wish, and you plug in for the t and the x and the y, you come up with a new solution and so on. All right, let's look at another example and another method, okay? So this is guessing for trial and error because the coefficients are very small, and we can do this. Let's look at another example. And here it is. Let's look at we have 525x plus 231y is equal 42. All right. Again, let's look at the greatest common divisor of 525 and 231. This happens to be as actually is equal to 21, which you can find by the Euclidean algorithm, and 21 divides 42. So this implies the equation has solution. And again, infinitely many. All right, now the question is, we need to find one of those, okay? So once again, we can divide the original equation by 21, both sides, and we come up with a simplified equation, which is just a 25x plus 11y is equal to 2. Once again, the greatest common divisor of the new coefficients is equal 1. And we would like to find numerical values for x and y to make this is equal to 2. Now, you remember by the Euclidean algorithm, all right, when we have the greatest common divisor is given to be a certain value, then there exists an x sub 0, a y sub 0 that give you a 1 in here, right? So by the Euclidean algorithm, there exist means you're going to be finding the greatest common divisor of 25 and 11 by doing this division algorithm several times till you come up with a remainder of 0. All right? So by the Euclidean algorithm, there exists, because this is U and V in Z integers, such that 25 U plus 11 V is equal to 1. All right? Now, I'm interested in solving this equation. 25x plus 11y is equal to 2. This one actually just came short of that. All right? So let's write what are those u and v that give me a 1. Okay? So in other words, we will find these from the Euclidean algorithm, and I'm just going to have the answer in here. So these values happens to be, they are not unique, but there are infinitely many values. So one of the values you get is 25 multiplied by 4 plus 11 multiplied by negative 9. In fact, this is equal to 1. Now then I claim that if you take x is equal 2 times 4, it's giving me 8, and y is equal to 2, that is the other side of the equation in here, 2, all right, times negative 9, which is negative 18, is in fact a solution for this equation, all right? And this will be also a solution for the original equation. So I claim that this is a solution for both the reduced equation and the original equation. All right, let's check. So in here, we're going to have a 25. Now let me actually leave this one as 2 times 4, okay? 2 times 4. Plus 11. And let me write this one as 2 times negative 9. Okay? Now, if you take the 2 common factor, as you can see, okay, so this is equal to 2, and then we have the original one, 25 times 4 plus 11 multiplied by negative 9. But this expression inside is equal to 1, so this is equal to 2, yes. Similarly, in here, we're going to be factoring out, the 21. Okay, so if you plug these back in, you get the solution. All right. Now, once we find this unique solution, then we can write what is the general solution. Okay. So now the general solution for, again, the reduced equation. Okay. So because of our general solution, or the solution set for this. So here the general solution is going to be x. The x sub 0 was 4 plus 11t, and y is equal to negative 9 minus 25t, the coefficient of x, where t belongs to the integers. All right? No, sorry. This is 8 and 18, because we multiplied by 2. Okay? This is 8, and this is 18. All right, the 4 and 8 these are the u and the v. This is what we obtain the solutions to the equation 25x, but we have to multiply it by 2. So we need these as a solution. But this, it's a solution to the original one, because the original one we multiplied by just 21 to get these coefficients. All right? All right, there is another method where it is more efficient than this method, where we use the Euclidean algorithm, and that this method refers to as Euler's method. All right, and I'm going to use this Euler method actually to solve this equation again. All right, we have Euler's method. And again, I will explain the steps of this method using this example. Once again, we're going to find the greatest common divisor and make sure that this equation has a solution, which we know it does. And also use this to reduce the equation. We could work with these coefficients as they are, but we better reduce the coefficients. So when I divide by 21, I end up with this equation, 25x plus 11y is equal to 2. Euler's method, it says, take the variable with the coefficient in absolute value is the smallest, okay, which is in this case the 11y. And we're going to solve this equation for y. So we're going to solve for y. So what do we get? We get 11y is equal to minus 25x. And then I'm going to be dividing by 11 to solve completely for y. So we're going to divide by 11. And I'm going to rewrite this, okay, by dividing the numerator by the denominator. Of course, 2 doesn't go to 11, so that's we're not going to get anything out of that division. But the 25 divides 11, we get actually 2 out of that, right? Or negative 2. So we're going to get negative 2, all right? And then the remainder, it's going to be the 2. And in here, we're going to end up with negative 3x. All right? Now, since x and y are integral values, we're looking at the values of x and y to be integer that satisfy this. This must be an integer in order for the y here that we solved for to be an integer. So we're going to name this integer a letter. Let me call this integer is actually the letter, let me choose t, okay? So we're going to, let me use actually a different than t. Let me use u, okay? So we're going to let t equal 2 minus 3x over 11. And this one supposed to be an integer. Now, let's make, from this a new equation. So if I cross multiply by 11, I get 11t plus 3x equal 2. So this is a new Diophantine equation, or we're going to, and now I'm going to repeat the process by solving for x, because the x has a smaller coefficient. Okay, so I'm going to solve for x in here. All right, let me put in, the t, I have this one in here. Let me put the equation at the top here, because we need to use this later on to check. Okay, so I want to solve for x. Now, this method becomes very, very important because when we look at the Diophantine equation in 3 variables, 4 variables, this is the much better method. Okay, so we're going to solve for x. Oh, so in here we're going to get x equal to 2 minus 11t over. Now, I don't want you to confuse this t with what the t we used in the solutions, okay, the general solution. This is just another 11 in here, over 3. And again, the 2 does not divide the 3, so I cannot do anything, but 11 I can divide it by 3. And this is going to give me, I hope I did the previous one correctly. Actually, I need, with the other one, actually, y, when I took the y in here, I wrote negative 2. Actually, it's negative 2x. All right, I'm sorry. So please change this to negative 2x. Then in here, 2 minus 3x over 11. Okay? And then I took this piece and I called it t. All right? The same thing in here. When I divide the 11, I get minus, let's see, 3. All right, 11 over 3 is a 3. And then we have a remainder. We have the 2, and the remainder is going to be 2t. 2t over 3. All right, so we have minus 9, minus 2, this is minus 11. All right, now I want to call this, and I call this is u. All right, and this is again an integer. All right, so we're going to have u equal to minus 2t over 3. And again, I want to convert this into a Diophantine equation, which is the 3u plus 2t equal 2. All right, I'm going to repeat this one more time, and we're going to solve it for t. All right. So we're going to solve for t. And we get 2t is equal to 2 minus 3u, and again dividing by 2. This is what we get. You get 1 minus u, then minus u over 2. All right? And finally, I want to call this one took a little more time. M equal, this is v. All right? And then this becomes t. Okay, so that's what we're going to call v. All right, so v is equal u2. Till we don't have, any division means, basically. We come up with, as you can see from this equation, that u is equal to v. And all of these are integers. And now we need to go backward, okay, and substitute for each one of these variables. So v being any integer, then from this one, we come up with the u, which I can substitute back in the t and get the value for that. Let me see where I can put our things in here. Okay, let me squeeze it in here. Okay. So we have, let's just start with v in the top is equal, actually u is equal to 2v. So this is the parameter. This is what we're going to express the solution in terms of. This one is u equal to v. Then we get to the x and the y. And then from this one, I can find what the t is. Okay? So t is equal to, doesn't make any difference where you substitute. We're going to substitute in this one, and we're going to come up with that 2 is going to cancel out. So it's going to be 2 minus 6v divided by 2, right? And this is equal 1 minus the 3v. Okay. Still, this is not, we are not interested in this. Then after this, we need to find what the x is. Okay? Here is the x, which is expressed in terms, or maybe even the y, actually. I took the y out. Okay, let me put the x, because I know how to find the x from here. So the x, I can substitute in here or this one. So let me substitute in here. So this becomes 2 minus 11 times 1 minus the 3b over the 3. So let's see what this is going to be. 2 minus 11 plus 33b over 3. When you subtract 2 minus 11, this gives you minus 9. And then divide by 3, you come up with x equal minus 3 plus 11v. Minus 3 plus 11v. So you got one of the variables, and then you need to find the y. I don't have it in here. I don't have it in my notes. So this is what it is. All right. It might actually take a little more than what I thought. I have another example that I was going to work it out. That actually it doesn't take as many steps. But it is a procedure that is not hard to kind of implement. You don't need to, well, it has some back substitution to it. All right, our next objective is to look at the positive solutions or sometimes non-negative solutions for Diophantine equations in 2 variables. All right? So let me start with a motivating example why we are interested in positive solutions. In fact, the Diophantine equations one of the purpose of it is to solve, problems of this type, okay? Because they don't admit solutions, all right, to be not whole numbers, basically. Suppose here's another example. All right, so suppose you purchase a candy bar for $1.15. Okay, and you give the cashier $2 bills, okay, two $1 bill. Unless you do have a $2 bill in you, okay? That's usually unlikely, whatever it is. Now the question is, in how many ways you get a change or the change you are supposed to get, which is 85 cents, get the change of 85 cents in dimes and quarters. Of course, if we allow some other types of coins to be used in the, in the change, this becomes a little more complicated. Okay, so I want to make it a simpler one. All right. Well, we can formulate, okay, answering this question into solving a Diophantine equation, a linear Diophantine equations in two variables. So if we let x represent the number of times, that's going to be in the change, and y number of quarters. Then the only solutions for when we write an equation, we want the x and the y to be whole numbers, right? And they cannot be negative, they could be zero, okay? Means we are looking for the non-negative, basically, solutions of an equation. Now, what is the equation in here? We want the amount, the value of the x is going to be actually 10x. And if you have in the change y quarters, this gives you a total of 25 y cents. And we want this is to equal 85. All right, so we are interested in solving this. Need to solve for non-negative integral solution, non-negative values of x and y. Well, when we know how to find all solutions to this Diophantine equation, first of all, you're going to see that the greatest common divisor of 10 and 25, which is 5, divides 85, so it does have a solution. So you have the greatest common divisor, 10, 25 is equal 5, and 5 divides 85. So this implies we have solution. And the method we learned, it gives us actually all the solutions, all right? So, first of all, to the equation, we can divide by 5. So we get 2x plus 5y is equal 85 divided by 5. I have 170, right? Let me check. Yeah. Now we need to solve it. And we're going to see after we solve it how to find the non-negative solutions. And then we will discuss some issues with the number of non-negative solutions. Okay. So let's use Euler's method. So we're going to solve for x in here. And then we divide. 17 by 2 is equal 8. And the remainder of 1. Then, the plus in here. And then the negative, or 5 divided by 2 is 2. All right. So we're going to end up with, no, I need the negative 2y in here, then a plus. We have a remainder of 1, right? And then from here, we have a remainder of 4, 1. And then we're going to be dividing all of this by 2. Actually, I did divide by 2. I'm sorry. This one is by 2. Then we're going to get u, well, this is u, 1 minus y over 2. Make this into a Diophantine equation, 2u minus plus y equal 1. Then solve for y. And we get y. And we are lucky because we don't need to work anymore in here. This one is 1 minus 2. So we don't have any fractions anymore. It looks like a fraction. All right? So we have the y and the u. And u is any integer. And now the x. Go back to the x in here. Is equal 8. We're going to just substitute. And I could substitute in either one of these forms. This one or this more stuffy one. So substitute for the y in here. So 17 minus 5, 1 minus 2u, the whole thing over 2. And simplifying and doing your algebra, you get 17 minus 5. That's going to be 12 divided by 2 is 6. And then we have positive 2u, 10u divided by 2 is 5 plus 5u. Okay, so we have this is the solution, all right? Take it out in here. So the solution for the reduced equation, which will be also solution for the original equation, x equal 6 plus 5u, and y equal 1 minus 2u, where u is an integer. Now, in order to find non-negative solutions, we need to find the values of u such that integer values such that the x bigger than or equal to 0 and y bigger than or equal to 0. Which is equivalent to saying that 6 plus 5u is bigger than or equal to 0 and 1 minus 2u bigger than or equal to 0. Well, let's solve both of these for u. These here are now inequalities. The first inequality is going to give me that the u is bigger than or equal to minus 6 over 5. And also I want, and the second inequality tells me that the u is going to be less than, because I have to take this to the other side, so u is less than or equal 1/2. Now we can put these in one inequality because the u appear in the two sides of the inequality, larger than, less than. So this is equivalent to u is bigger than or equal minus 6/5, and this one less than or equal 1/2. Now how many, and u is an integer, right? U is an integer that is in this range. So the only value of u that is in here, okay, u must be -1. All right? Now with our solution, there's only one value. Well, actually, let me see, one value or two values. Actually, two values, I'm sorry, two values. U equal and 0, two values. Because, -1, and then we have 0, and then we go to the positive. All right, and this gives me two different or two possible actually change for the I think x for this one you get x equal 6 minus 5, which is 1 dime, and the y is equal to 3/4. This one you get x equal 6 times and 1/4. And you know that this is the right change, right? And this is the only one in it, all right? Now, one last issue I want to discuss is the number of these non-negative solutions, okay? And I'm going to leave this, I'll write it again. Okay, let me start again in here. All right, we want to discuss the number of non-negative solutions. In fact, we could find the formula for this number, but again, the derivation is going to take us very far. Not very, very far, just a little farther than, what I need to actually go do. I don't want to do it very long, because I want to discuss also something, and it's not in the textbook, that is solving the Diophantine equation, linear ones, or 3 variables, 4 variables, and so on. So I want to restrict myself to a very brief discussion in it for the number of, non-negative solutions. Basically, we're going to see, are there infinite or infinite? And the finite means even none in here, okay? It means also could be have none, no solutions at all that are non-negative. Now, in general, we know that ax plus by equals c. This represents a straight line. A straight line. With slope is equal to actually negative b over a. All right? Make sure that actually negative a over b. You can rewrite this one in negative a over. Then I'm not even interested in there. Let's go to slope m. Now, if m and m does not equal to 0, because we are assuming neither A or B is equal to 0. So we have a line that has actually an x-intercept and a y-intercept. If M is positive, then the line, one possible, okay, graph of such line looks like this. It has a positive slope, so it could be coming, as we trace the graph from left to right, the line is going to be actually rising up. It could be going this way, it could be going that way, but it's rising up. Now, in this particular case, as you can see, an infinite portion of the graph is going to be in the first quadrant, okay? So it's not horizontal, it must be rising up. And in this case, if there is one positive solution or non-negative solution, means a point of intersection of either the coordinate axis or a point which is on the line with it's a lattice point, then there are infinitely many. So in this case, either there are no integral solutions, positive or non-negative integral solutions, non-negative integral solution, or the other extreme, there are infinitely many. Okay, does this picture actually explain why this is the case? All right. As I said, there is a formula you could actually count when it is finite, but in this case, we only have actually none or infinitely many. Just once we have one, then as you know, we can generate infinitely many because you could take the values of the t, all right, to give you positive numbers from some point on. Okay. On the other hand, if m is negative, okay, let me see it here. Let me take all this off. Now, if the slope is negative, then a possible graph, or the graphs in this case they are going to be falling down. It's a straight line falling down. All right? And it could be going this way, so we don't have any, or it could be going this way, or it could be going much farther up. And as you can see, we either have none, all right, or only finitely many, because this portion, all right, even if this line goes very, 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 very far, it's still a finite number. Okay, because what's going to be in the first where it intersect, or the portion of the line that actually intersect the x and the y axis in the first quadrant. Okay, so in this case, there is no non-negative. And among the no in here, because the equation itself does not have any solutions, basically, the Diophantine equation. Of course, it's not going to have any non-negative solutions. Or a finite number. All right. Now, if we look at that, at the example that we actually did work for the change for 85 cents, we're going to see why we got a finite, because the slope is negative. All right. And of course, you know when the slope is negative based on the A and the B, you could actually write a rule for these. So with this example, it was 10x. Let me see what was the example in here. Yeah, the 10x plus 25y is equal to 85. And the slope is negative, actually A over B. And the graph is going to be actually falling down. So it's going to be this. You could find a more accurate graph, but it's going to be negative and it's going to have a finite number. All right. Actually, the 2 points that we got in here is 1 and 3. And then we got 6. My picture is not accurate, as you can tell. So maybe the slope is actually negative 2/5. So it's going to be a much not a very steep line. So we got 1 point, which is 1 and 3. And another point is 6 and 1. Maybe something like this. So these are the only 2 lattice points that this line actually processes. All right, at least in the first one, but there are infinitely many in the third and fourth one. All right. All right. Let me see if I want to stop here or. Yeah, I want to finish up with this. Might take a little more time, but not very long. So the next thing I want to do is to look at the Diophantine equation in n variables. Okay. The question is, do we have a necessary and sufficient condition for their solution? What type of solutions they have? Okay. So linear Diophantine equations in variables. All right. Again, such an equation is going to look like this: a1 x1 plus a2 x2 an xn equal c, where all the coefficients here, the a's are constant, they are integers as well as c. The question is, under what conditions this equation is solvable? And we're going to see it is the same. All right? That is the greatest common divisor of all the coefficients must divide the constant. And once this equation has a single solution, it has infinitely many solutions. So we're going to state this is as a theorem. And actually, just to save the time, I'm not going to actually present the proof. Okay? The proof is basically based on mathematical induction. It is not very hard. It is a little long. All right? Just I don't have the time for it. Okay? So let's just state this is as a theorem. But you are welcome to use this theorem. Okay? And it says that the equation above is this one in here. an integral solution if and only if greatest common, if I say D is equal to, take this one out, the greatest common divisor, A1, A2, up to AN, must divide C. In this case, means when it divides, the equation has infinitely many integral solutions. And let me just put as a reference what I said, the proof here is by math induction on n, number of variables, all right? So we know it's true for two variables, then we can assume it's true for, actually it's true for even one variable, all right? It's true for two variables from a previous theorem, and then assume it's true for k variables and prove that it will imply that it's true for k plus 1 variables, all right? Actually, the method of solution is basically how the proof goes, okay? So let me illustrate this theorem by solving at least one example, maybe two, of a Diophantine equation in the three variables. Now, as you can tell from the way we're going to solve this, this could be a time, time consuming to solve by hand, okay, a Diophantine equation in 4 or 5 variables. All right? So let's look at a simple example to start with, and then look at another example. All right? So let's just start by looking at this. Okay, we're going to solve 15x plus 12y plus 8z is equal 400. Now, when you look at the greatest common divisor of 15, 12, and 8, this is going to equal 1, all right? With our divisors of this is 3 and 5. This is divisors of this 3, 2, 4, and so on and so on. So they don't have a 5, at least in all of those, okay? Or a 3 in the 8. So this is it. So we're going to reduce this. We're going to apply actually Euler's method. Okay, to solve this. And we also want other thing. Even remember from your days of linear algebra, if you are given an equation in, first of all, two variables, that the one which we did, the solution is going to depend. We don't get a unique solution usually, right? We get no solution or we get infinitely many solutions because it's a linear equation. And the solution depends on one parameter if it has infinitely many. Now, if you have an equation in the three variables, the answer is going to depend on two parameters. We're going to have a t and a u, so two parameters which we express the x, the y, and the z in terms of. All right? And we're going to see this one in here. So what is Euler's method? It says take the variable with the smallest coefficient, okay? And if there is a tie, you could pick one, and solve for it. So we're going to solve for z. And this is what you get after you simplify and solve. And I want to save the time in here. And we're going to divide by 8, so you're going to be dividing everything by 8 and pull out any integral parts of the number, the x and the y, and then you're going to end up with an expression like this, which doesn't divide anymore. As you see, none of these crosses. Now we know that all of these are integers, so we're going to name this. Let me call this one is actually u. So we're going to let u is equal 7x plus 4y over x. Now with this, of course, we have the z now becomes equal to, we could write it here, 50 minus x minus y minus u. Okay? Now we're going to turn this into a Diophantine equation itself. So we get 8u, and we arrange it like this. 8u minus 7x minus 4y, 4y, okay? And so 8 minus is equal to 0. All right? Now, once again, here we're going to solve for the y. Okay, so from this one, we get y is equal to, again, after you divide and simplify and so on, you get 2u minus x minus 3x over 4. Okay, we need to name this a letter, and I'm going to choose for this is v. So I'm going to call this is v. So this becomes 2u minus x minus v. Okay? All right, we move up. And we're going to solve this time for, we're going to set this is equal to v. And we're almost there because I don't have any fractional parts in it. So we're going to make this v is equal minus 3x over 4. And from here we get, now actually still we have to do one more. 4v plus 3x equals 0. And then I need to solve for x. Okay? I'm going to solve for x. And what do we get for x in here? We get v plus v over 3. Okay, so when you add up, we come up with this equation. Do we have a negative in here? Supposedly. Actually, let me, yeah, this one is in the negative in here. So we have this is positive. All right? And with this, then we have this equation in here. Then one more thing. And I want to then call this, okay, t. All right? So the last thing is we're going to have v over 3 is equal to t. And this gives me v equal to 3t, thanks God. All right, so we have an integral value, okay, where p is and t is in z. Now we need to go back and substitute for the v back in here in terms of the t, and you get your x. So you get your x equal to 3t plus 3t over 3. So this gives me 40. Your y, where's the y? The y is still, first of all, you need to find what the u actually is going to stay in here. So the y is going to be equal to, again, cheat and put the answer in here. You get 4y, 2u minus 7t. And for the z, when you substitute back to the very, very top one in here, okay, So you have this is expressed in x, y, and u. So you have x and y expressed in t and u. So when you do this, you get this for z. So the z is equal 50 plus 3t minus 3u. All right, one last thing, okay, to compare the answer we are getting for these, because these are linear equations. So we could express the answer in matrix form or vector form. And it actually, if you remember, the type of general solution you get for a system of linear equations. So the solution x, y, z. Well, we have this one is written like this. Let me write it as is. This is 4t. This one is negative 7t plus 2u. And the z is 50 plus 3t minus 3u. If you make each one of these has a constant, has a u and a t, so you would say this one is equal 0 plus 4t plus 0u. Make this is the same, it has no constant, means 0 minus 7t plus 2u. And this one is 50 plus 3t minus 3u. You can split this into a sum of 3 vectors. And all of these is a multiple of t. And these is multiples of u. Just put the coefficients in here. And so this is the solution expressed in a form that is similar to what you do here in algebra. So the solution set basically consists of these where we have 2 parameters, t and u are in z. And by the way, for you to check this, actually form a solution for the homogeneous equation associated with this equation. And the homogeneous equation, which we make the right-hand side, is equal to 0. So if you take this equation, original equation, and you substitute for x, y, and z by this, you come up with actually, as you see, let's see, a particular solution. This is a solution. Scratch what I said about homogeneous. This is actually a solution for this. And this, the rest of this, is a solution for the homogeneous. Means this side is equal to 0. So if you plug in, all right, just add up these 2 solutions and you plug in for x, y, and z, you're going to see that the t eliminated and you get 0. Okay? Well, I'll leave that for you. But this is, of course, further from general consideration. All right. I hope this is clear. I was going to work another example using actually again Euler's method. But there is an alternative method which you could use as well. Let me point out to it, okay, with another example, and come up with one solution. Here it is, very short. Where you find the greatest common divisor. I don't want to do all the details, but I'll put enough details hopefully to become clear. Suppose we want to solve this equation. (76y plus 42z is equal 80. First of all, the greatest common divisor, we we can take for all of them and find that it does divide 18. Okay? Then what we want to do, we're going to take the greatest common divisor of these. That's 76. And this, it turns out to be 36. Then we can use the Euclidean algorithm to express 36 as a combination of the x and the y, okay? Sorry, the 252 and the 576. That's the one we can, we found their greatest common divisor, supposedly using Euclidean algorithm. So what you find that you could write 36 as 252 times 7 and 576 times negative. Then you take the greatest common divisor of 36, the one which we had, and 42. Okay? And this one happens to be equal 6. And then you express 6 as a combination of multiples of 36 and 42. Okay? Doing this back substitution, all right? You find the this can be expressed as 42 times 1 plus 36 times negative. Then you wanted, which is the 6, it happens to be the greatest common divisor of actually 4 there. So the greatest common divisor of 252, 5, because this is the way we find the greatest common divisor of a 3. And we find for 2, and then we use that with the third one. So this is equal to 6. Now the question is, can I express 6, all right, in terms of, in other words, we're going to use these two equations to express 6 as a linear combination of the original coefficients. And you find that this is by substituting, so you get first of all 42 times 1, we don't have any 42s in here, and then you're going to replace the 36, all right, by what is 36 is equal to. So this is 36. So I want to take this, actually, the 36, I want to express this, and then we have a negative 1 goes with it. Okay, so we're going to have 2 plus 252 times 7 plus 576 times negative 3. All of this is the 36, remember? And we need to multiply it by negative 1. And then we, from here, we would have a value for x, y, and z. We need to multiply by 3 to get, so we need to multiply this is by 3 to get an 18. Now, then you will get your x, your y, and your z after you multiply. So the net result you're going to see actually is, well, I'm just going to leave this for you. Actually, we're going to get as a solution, let's see it here. For this one is a 3, and for this one, 21 minus a 21, and for the y, that is going to be minus 9 plus 9. And this becomes solution to the equation. Okay? All right? The reason we want to multiply by 3 to get this 18 in here for the greatest common divisor. Because these are what give me 6. And now when I wanted to 18, I need to multiply by 3. All right, let's stop right here.